Okay, in this video we are going to do some challenging, but not insanely challenging, antiderivatives. There should be a link in the description to the problems that we're going to do with timestamps. And if you find that I'm going too quickly for you, feel free to slow down the video. Alright, let's get started. So first integral that we're going to do, the integral of x cubed over x squared plus 1 dx. So if it's a rational function and the numerator has a higher degree than the denominator, then we have to rewrite it. So I'm going to do division, and let's see. So I'll do that over here. So x squared plus 1. I like to put in placeholders so that everything kind of like lines up by column as I do these things. So that's why there are all those 0, x squared, 0x, 0. All right, so I need to multiply by x. And if I do that, I'll get this, and put in parentheses and subtract. And so this just gives me negative x, and that's a lower degree than x squared plus 1, so I'm actually done with the division at this point. So I'm going to rewrite the integrand. So we're integrating x, and then minus x over x squared plus 1 dx. And so I can definitely integrate the first part there. That's 1/2 x squared. And then here, okay, so it's integral of this, and this to me looks like a natural log. I would let u equal x squared plus 1, and then go from there. But since this comes up so often, I'm just going to kind of do this the way I would usually do it. So the derivative of x squared plus 1 is 2x dx. So I need a 2 in the numerator, and then to balance that out, I just put a 1/2 on the outside. And now it's like a perfect antiderivative situation. That's perfectly the derivative of the natural log of x squared plus 1. So we can write our final answer here. So it's 1/2 x squared minus 1/2, and then we integrate this, and we get natural log of the absolute value of x squared plus 1. You can drop the absolute value there because x squared plus 1 is just always positive. But I'm going to leave it in anyway because I think it's a little safer. Definitely a good habit to get into, putting those absolute values in there. All right, let's take a look at the next problem. So it's the integral of radical e to the t minus 3 dt. Okay, so with problems like these, usually what I do is just let u equal the integrand. So I'm going to let u equal the square root of e to the t minus 3. If you do a lot of problems, eventually you develop habits like that. So I just know that this is going to help me out. Like, it's going to turn into an integral that doesn't have a radical, which is generally speaking easier to work with. So let's see. I'm going to, so before I find like a du or a dt type thing, I like to kind of like get everything out of the way. So I'm going to square both sides here. Get u squared is e to the t minus 3. And then I'm actually going to add 3 to both sides and just get u squared plus 3 is equal to e to the t. So I'm doing that because it's going to kind of isolate the dt that I'm looking for. So I'm going to have that, and then 2u du is e to the t dt. And I know what e to the t is. E to the t is u squared plus 3. That's the thing in the box. So I can actually just say that 2u du over u squared plus 3 is equal to dt. And that's another thing that I'm going to substitute. Okay, so let's go back to our integral and rewrite this thing. So our original looked like this. And now it's going to be the integral of, that whole radical is just u. And then dt is 2u du over u squared plus 3. Okay, so it's kind of a messy looking integral, but I'm going to clean that up. So 2u squared over u squared plus 3 du. And this is the same situation. I got to do division again. So let's do that over here. So putting in some placeholders just to potentially make it look cleaner. So if I multiply by 2, I get 2u squared, and then plus 6. And then if I simplify that, I just get negative 6. So it's going to be 2, and then minus 6 over u squared plus 3. So let's rewrite this. So it's the integral of 2 minus 6 over u squared plus 3 du. And we need to integrate this. So remember, it's with respect to u, so the integral or the antiderivative of 2 is going to be 2u. And then I actually see a lot of people make a mistake on that, by the way. Like the original problem is in terms of t, so they'll just say that that's 2t, but it's not. It's all, everything is in terms of u, so it's 2u. And then what should we do here? I'm going to rewrite the integral. I'm going to divide everything I see in the integral by 3 because it looks kind of like arctan to me already because of that u squared in the denominator. So minus, so dividing 6 by 3 gives me 2. And then I'm going to rearrange it to be 1 plus the quantity u over radical 3 squared, which if you expand that is just 1 plus u squared over 3. And you can see that I definitely divided u squared by 3. But since I was already thinking it was arctan, I always jump to that like quantity squared. Okay, so what do we do here? If it's perfect, I would have I'm not really worried about that 2 in the numerator because that's a constant multiple, so I can just factor that out if I need to, which I do. But if I had a 1 over root 3 in the numerator, this would be a perfect arctan derivative. So I'm just going to put it in, but I have to balance it out with a root 3 on the outside. And I'm also going to end up factoring that 2 out. So let's see. So we got 2u minus 2 root 3, and then arctan, or inverse tangent if you prefer, of u over root 3, and then plus c. And now we just replace u with radical e to the t minus 3. So we get something that looks like this. And this is not going to clean up at all, so this is it. There, and then plus c. There you go. All right, let's take a look at another problem. Integral of x times the quantity x minus 1 to the 10th dx. So we're going to end up doing a lot of problems that kind of look like this, where you have like crazy powers. I guess 10th power I think is a pretty crazy power. Usually what you do on these is you let u equal the thing inside kind of the highest power so that you can avoid dealing with that. Like I wouldn't want to expand x minus 1 to the 10th. So I'm going to let u equal x minus 1. And then in the integral it'll just be u to the 10th, and that's good because there's like nothing to be done with that. So this, I'm going to solve for x because I actually have to replace x in the original. So this is one of the things that'll be subbed in. And then from here I get that du is equal to dx. That's another thing I'm going to substitute for. And now let's just do it. So we're going to make our substitution. So x is the quantity u plus 1. X minus 1 is u, so this becomes u to the 10th. And then dx is just du. All right, I'm going to expand. So we get u to the 11th plus u to the 10th du. Reverse the power rule. So we have 1/12 u to the 12th, 1/11 u to the 11th, plus c. And then I can just let u equal x minus 1. But you might be looking at that and saying, like, I have a u to the 12th and a u to the 11th. I could definitely factor out u to the 11th. I'm going to also do that. So I'm going to do this 2 different ways. So the most expedient way is to just do this. And then you kind of just look at your answer and you're like, yeah, that's the antiderivative. But it's not factored. So this is one option. A second option, so if you're going to factor these sorts of things, this isn't bad because the exponents are rational numbers. No, not rational, they're integers. When they're rational exponents, it's kind of annoying to factor the like substituted version. So I'm going to go back a step and factor this. So take out u to the 11th. We get this common denominator. We get this. Then we know that u is actually x minus 1. So we can substitute. And then here we're going to be able to clean this up like that. And then finally we just kind of like, simplify that a little bit. So 11x plus 1 over 132, and then plus c. So when you do these problems on your calculator, there's like no guarantee which of the two it's going to kind of spit out. I tend to think it'll spit out the second one, but be aware, they're definitely equivalent, and you can do it either way. So let's take a look at another problem. Okay, so we have the integral of sine over 7 plus cosine squared of x dx. When I look at this problem, I initially kind of thought it might be a natural log, but then the derivative of, so if it's a natural log that we're going to end up with, then u would be 7 plus cosine squared of x. Du is way more complicated, well, not way more complicated, more complicated than just sine of x dx, so that's not the way to go. So then I start thinking like, okay, so sine is definitely the derivative, well, sine is like the derivative of cosine, but I have cosine squared, so now I'm thinking arctan because I have a fraction, so I'm going to try to turn this into an arctan. So to do that, I need to get a 1 in the bottom left, and that means dividing everything I see by 7. So it's going to be sine of x over 7, and then 1 plus, and I'm going to do that thing again where it's cosine of x over radical 7, and then squared. So cosine of x over radical 7, square the whole thing, you get cosine squared over 7. It's just, if you know it's going to be arctan, that's like a little faster. So let's see what we can do here. I'm going to pull out the 1/7 that's in the numerator and get this. And then I'm going to kind of do the whole balancing act, right? So if u is equal to cosine of x over root 7, then du is negative, if u is equal to cosine of x over root 7, then du is going to be negative 1 over root 7 sine. So I need a negative 1 over root 7 in the numerator, and then I'm just going to balance it out with a negative root 7 on the outside. So those, if you multiply them, you would get 1, so you're allowed to do that. And now it's perfect. So it's going to be negative root 7 over 7. And then this is a perfect arctan derivative at this point, so it's going to go back to the arctan of cosine of x over root 7, and then plus c. All right. That one wasn't so bad. You just have to kind of like, you end up going through that process a lot where you look at an initial integrand and you think, maybe it's natural log and then it doesn't work out. Maybe it's arctan, it doesn't work out. Maybe it's just regular u-Substitution and it doesn't work out. And you just kind of keep going through the list. That list was backwards, by the way. I usually initially think maybe u-Substitution will work. If that doesn't work, maybe it's a natural log. If that doesn't work, maybe it's arctan. If that doesn't work, you usually need to like break out something even more complicated, which isn't the point of this video. So let's take a look at another one. Okay, it's the integral of x minus 2 over the quantity x plus 1 squared plus 4 dx. So I look at that and I see that quantity in the denominator and I think this problem would look a lot simpler if that wasn't there. And because I think that, I'm going to let that be u. So u is equal to x plus 1. So that means that u minus 1 is equal to x. And I'm going to use that to figure out dx, but also I'm going to make a substitution with that. So that's one of the things we're substituting, because in the numerator there's an x. So I'm going to replace that with u minus 1 and end up with u minus 3 in the numerator. But let's keep going here. I need to find du. And du is just dx, which is always a good situation. So here, let's make our replacements. So in the numerator, I let x equal u minus 1. U minus 1 minus 2 is u minus 3 over x plus 1 is equal to u. So this became u squared plus 4. And then dx is du. So we have this. This I'm going to break into two separate fractions. So this is a common thing to do when there's a sum or difference in the numerator, is to try to break it into two and hopefully do each of the integrals separately. Often when that happens, you get one arctan and one natural log, which I think is actually going to happen here. And then minus. I'm doing the thing where I pull 1/4 out and turn this into a perfect arctan type of situation. So what I did was I took the 3 out of the numerator, and then I divided everything I see by 4, which gives me a 1/4 in the numerator, and then over 1 plus u squared over 4 in the denominator, and I just kind of rewrote it, took out the 1/4, so I've ended up here. I probably should have shown more work on that one. If you expanded this or distribute, you would end up back here, which is kind of where the original was. All right, so let's do some integrals. The first one looks like a natural log to me, but I need a 2, and so a 1/2, and now it's perfect. So it's 1/2 natural log absolute value of u squared plus 4, and then minus 3/4. Now I got to integrate this thing. So if I don't know, like w, let's say w is u over 2, then dw is 1/2 du. So I actually need a 1/2 in the numerator, and therefore a 2 will be on the outside. So that's where that 2 is coming from, and then it's a perfect arctan. This plus c. And then I'm just going to replace every u with x plus 1, and that'll be the end of this integral. So we get 1/2 natural log absolute value of x plus 1 squared plus 4, which is actually always positive, so you could drop the absolute value, but I'm not going to. And then, so negative 3/4 times 2 is negative 3/2, and then arctan of x plus 1 over 2 plus c. All right, that was a pretty good one. Let's take a look at another one. So, integral of x root 4 minus x dx. When you do these problems, it's usually the case that like things that are in a quantity are what's causing you a problem. So here, that radical, the thing inside the radical is causing me a problem because it's 4 minus x, and that's a little weird. So you have two choices. You can make u equal 4 minus x, and then it'll just be the square root of u, which isn't really bad. Or you can make u equal the entire radical, which kind of has some advantages because you end up with integer exponents. So I'm going to go with that method, but the other method would totally work. So if you want to try it on your own, like, go for it. So I'm going to make u equal radical 4 minus x. Square both sides. So I don't want to mess around with finding dx yet because x is kind of nested in a radical and there's some chain rule stuff you'd have to do. So I'm going to say that u squared is 4 minus x. And I'm actually going to go one more step. I'm going to add x to both sides and subtract u squared to get that x is 4 minus u squared. Now I'm going to, well actually, if you look, we need to replace an x in the original problem. So I'm going to end up using this for a substitution, and I'm going to find dx here. So dx is negative 2u du. Okay, so let's make our substitutions. So it becomes x, we said, was 4 minus u, so we're going to have the quantity 4 minus u squared, 4 minus u squared, and then the whole radical we made u times u, and then dx is negative 2u du. So make sure you do all of those substitutions. A lot of people, when they do these sorts of problems, they end up losing a u somewhere along the way. It's really important that it be there because obviously it's impacting the problem. Let's just clean this up. So I'm going to take out a negative 2 and distribute the u squared. So I get this. And now I'm going to reverse the power rule. So negative 2, 4/3 u cubed, minus 1/5 u to the 5th, and then plus c. So we're done in terms of u, but we're not done in terms of x. This is you have a branching path in front of you. You can directly substitute, which is a good idea, or you can factor this and then substitute, which is also a good idea. So I'm going to do both of them. So I get negative 8/3, just distributing that, and then it's 4 minus x, well, it's radical 4 minus x, but I'm going to think of it as 4 minus x to the 1/2, and then multiply the exponent, so I get 4 minus x to the 3/2. So that's where this is coming from. And then it's negative 1/5. Oh, sorry, no. Distribute that negative 2. So it's negative 2 times negative 1/5 is positive 2/5. And then same thing here. So it's 4 minus x to the 1/2, and then to the 5th. So 4 minus x to the 5/2. And then plus c. So this is one form that the answer could definitely take. But if you go back a step, you can factor a u cubed out of everything. So I'm going to do that. And then if I do that, let's see what's left. We get 4/3, then minus 1/5 u squared plus c. U squared is a nice thing to have because U is radical of 4 minus x. When I square it, the radical goes away. So we have this. Common denominator here. So 20 minus 3u squared over 15. Let's do our substitution. So we're going to replace u with radical 4 minus x, but we think of it as 4 minus x to the 1/2 because it's a little cleaner that way. Then when you square radical 4 minus x, you just get 4 minus x, so that's where that's coming from. And then finally, we can distribute and collect like terms inside that final parenthesis there. So we end up with 3x plus 8 over 15 plus c. So that's another form that it could take. Either of those, totally valid. All right, let's do another one. We're going to do 21 of these, so this is going to be a long video. So it's the integral of x squared over the quantity x plus 5 cubed dx. I've said it several times, quantities are kind of a problem, especially when they're in denominators. So I'm just going to go ahead and let u equal x plus 5. I need to actually substitute for x squared, so I'm going to solve this thing for x and say that u minus 5 is equal to x. And I'll be able to substitute that for x and then square it, and that'll be okay. And then from here, so this is a substitution, and then from here, I know that du is dx. Okay, so let's do our substitutions. So we get x, which is u minus 5 squared, and that's over u cubed, and then du. So this one, I don't think there's like any tricks to it. I'm just going to expand the numerator and then basically break it up into 3 integrals and try to do each of them. So we get this. So this, I'm going to think of it as 1 over u minus 10u to the negative second plus 25u to the negative third du. I left it as 1 over u because u to the negative first, I would be inclined to try to reverse the power rule, but it doesn't work on that because you get u to the 0 and then times 1 over 0. Like, what's going on? Every time that happens, it's actually just natural log, so that's why I left it as 1 over u. Let's find antiderivatives. So the first one is natural log absolute value of u. The next one, reverse power rule, so plus 1 gives you negative 1 times reciprocal, so we end up with plus 10u to the negative first. This one, reverse the power rule, add 1 to the exponent gives you negative 2, times the reciprocal is negative 1/2, so we get minus 25 over 2, and then u to the negative second, plus c. And I'm actually just gonna substitute here. I'm not gonna like try to get a common denominator amongst those things because like nothing good is gonna happen. So I'm gonna rewrite it, but I'm not gonna use negative exponents because I don't know, I'm kind of biased against those. So I'm gonna get 10 over, and then u is equal to x plus 5, and then minus 25 over 2 times the quantity x plus 5 squared plus c. All right, so that's a 7th problem. Let's take a look at an 8th problem. Integral quantity x plus 2 times the quantity x plus 1 to the 1/4 dx. You might think you have a choice, like maybe I should make u equal x plus 2, but if I make u equal x plus 2, then I still have a problem with that thing to the 1/4. So instead, I'm going to try to make that simpler. It's just like if it was to the 53rd power. I would definitely want to make u equal x plus 1, so that's what I'm going to do. So when you make substitutions, you do them to make your life simpler, right? So don't make a substitution that makes your integrand worse. So here, let's keep going. So u minus 1 is equal to x. I'm going to need to substitute that because of the x plus 2 part. And then from here, I know that du is dx. So I'm going to substitute that also. So let's rewrite. So it's the integral of, so x plus 2, x is u minus 1. So it's u minus 1 plus 2, so this becomes u plus 1. And then the whole idea was to make that u. So u to the 1/4, and then dx is du. Okay, distribute, and then we're going to integrate. If you've been following along, you might get the sense like, yeah, this is another one of those where like probably we can write the answer 2 different ways. So let's reverse the power rule. So plus 1 times the reciprocal, and then again, plus 1 times the reciprocal, and then plus c. So basically done if we just make our substitution for u. We would get 4/9, and then quantity x plus 1 to the 9/4, plus 4/5 the quantity x plus 1 to the 5/4, and then plus c. But that's probably not the answer that a calculator or a computer would give you. So instead, let's go back a step, factor it, and go from there. So you can actually, so you could take out 4u to the 5/4, but I only took out u to the 5/4. So u to the 5/4, and what's left over? So 4/9 u to the first power, because if you take out u to the 5/4, you're left with u to the 4/4, which is u to the first, and then plus 4/5. You can kind of see like leaving that 4 in there just makes all the calculations a little bigger, so it's kind of a bad idea. Probably should have taken it out, but I didn't. Okay, so let's keep going. Common denominator here, going to be 20u plus 36 all over 45. Okay, at this point, I am going to take some things out. So I can take out a 4 and that 45 in the denominator. It just makes it look so much cleaner. So I've done that. And then u is equal to x plus 1. So if we make all of our substitutions, in that second one you get 5 times the quantity x plus 1 is 5x plus 5, and then plus 9, so 5x plus 14. Plus c, that's probably more the answer if you type it into your calculator that you're going to get. So that's why I wanted to do that. Let's take a look at another problem. Okay, we're doing the integral of 1 over x cubed radical x squared minus 1 over x squared dx, which is kind of like a weird way to write something to begin with. It's like deliberately trying to obscure what's happening by not simplifying that. So what I'm going to do is simplify that x squared minus 1 over x squared and see if it makes it look a little less scary, because this looks like a scary integral when you first see it. So here we go. 1 over x cubed, and then x squared over x squared is 1, and then it's just minus 1 over x squared dx. And now things are looking a little better, right? Because the derivative of 1 over x squared, so that's x squared to the negative second, is negative 2x to the negative 3, which has a x to the negative 3 in it, which is really good because that's actually sitting there in front of the radical. So we'll make u equal 1 minus 1 over x squared. And in that case, du is, so it's 1 minus x to the negative second. Derivative of 1 is 0. The derivative of negative x to the negative second is positive 2x to the negative third, just power rule. But I'm going to rewrite it like this. And then I like to solve for what's in the problem. So in the problem, there's a 1 over x cubed and a dx. That 2's got to go, so I'm going to move it to the other side. So I'm going to say 1/2 du is 1 over x cubed dx. We're going to substitute that, and we're going to substitute u for 1 minus 1 over x squared, and totally change our integral. So we get, we end up with actually just, so 1 over x squared, 1 over x cubed, sorry, dx is 1/2 du. And then the whole idea was we were going to make 1 minus 1 over x squared equal to u. So this is our whole integrand. So it turns out like it's an easier problem than it initially looks like, but it looks scary. Plus 1 times the reciprocal to get this, plus c. I'm going to simplify the 2/3 and the 1/2 down to just 1/3, and then do the substitution. So I get 1/3 the quantity 1 minus 1 over x squared to the 3/2 plus c. Okay, and now we're going to take a look at another problem. Integral of e to the x over e to the 2x plus 2e to the x plus 1 dx. Okay, the only way to get good at these problems is to just do a lot of them. I look at this problem and I think that denominator is factorable, so I'm going to try to factor it before I do anything really. So we get this. So it's like, so if e to the 2x is just e to the x squared, so it's e to the x squared plus 2e to the x plus 1, that's actually just a perfect square. Like that, it's e to the x plus 1 quantity squared. And now I'm going to let u equal that quantity in the denominator, because quantities in denominators are tough to deal with. So u is equal to e to the x plus 1, which means that du is going to be e to the x dx. So that e to the x in the numerator is going to get lumped in with du, and this integral is going to end up looking pretty simple. So it ends up looking like du over u squared, which you might rewrite as the integral of u to the negative second du, and then plus 1 times the reciprocal gives me negative 1 over u plus c, and then u is equal to e to the x plus 1, so we get this. Okay, let's take a look at a new problem. Number 11, the integral of the square root of x cubed minus 3 all over x to the 11th dx. Okay, so this one looks crazy, but if you've been doing all the problems, it looks an awful lot like problem number 9, and so I'm going to try to take advantage of that. Like, I'm going to try to make x cubed minus 3 over x cubed happen, and then take it from there and hope that it's really similar, because that's actually the secret to doing a lot of antiderivatives well, is if you've already done one that looks exactly like it, you pretty much know what to do. And I'm thinking this is exactly like number 9 was. So I'm going to break up this denominator into x to the 8th times x cubed, because that'll do it. And then rewrite it a little bit, just trying to make it clear what's happening. So I'll make it 1 over x to the 8th times x cubed minus 3 over x cubed dx. The square root of 1 over x to the 8th is actually just 1 over x to the 4th. And then this we can simplify to 1 minus 3 over x cubed dx. And now we're ready to do the problem. So I'm going to let, so all of that like is a part of doing the problem, but not a part of doing the antiderivative. That's just algebraic manipulation to make it look a little better. So now I'm going to let u equal the thing in the radical, because I know from experience that this is going to help us out a lot with that 1 over x to the 4th, because when we find du, we get 9 over x to the 4th dx. So there's no 9 in the original problem, so I'm going to bring the 9 to the other side and let it just like be substituted with du. So 1/9 du is 1 over x to the 4th dx. That's something we're going to substitute. Okay, so going to replace, what am I replacing? So 1 over x to the 4th dx is 1/9 du. So there's the 1/9, and then I'm going to put the du at the very end. It's going to be square root of u, or u to the 1/2, and then du, because that 1/9 du is 1 over x to the 4th dx. So that's where those parts are all coming from. And now it's not that bad, right? We're going to have a 1/9. We're going to reverse the power rule. So 2/3 u to the 3/2, and then put plus c. And this we can simplify. So 1/9 times 2/3 is 2/27, and then replace u. So 2 over 27, 1 minus 3 over x cubed to the 3/2 plus c. There you go. All right, let's take a look at another one. We've got the quantity, or the integral of the quantity x plus 2 squared times the quantity 1 minus x to the 5th dx. So when you have to make a choice between something to the 2nd and something to the 5th, you would rather do something to the 2nd. So we're going to let u equal the thing that's being raised to the 5th power. So u is equal to 1 minus x, which means that x is equal to 1 minus u, and we can use that to find dx. Okay, so we have dx is negative du. I'm also going to use the fact that x is 1 minus u, so I should have put a box around that, but I forgot. So let's make some substitutions. So it's the integral of u is equal to 1 minus x. So I have 1 minus x. Oh, no, x is equal to 1 minus u. Sorry, doing a weird substitution there. So x is equal to 1 minus u. So I have 1 minus u plus 2, so 3 minus u. Quantity 3 minus u squared. And then it's u to the 5th. And then dx is negative du. So I'm going to put the negative on the outside and a du on the inside. So we have this. I don't think there's anything special to do here, so I'm just going to expand. And and kind of just carry through some algebra here. So distribute that u to the fifth to get this. And let's go through and reverse the power rule a bunch of times. And let's see, so we're going to get, you end up with 9 over 6, which is 3 halves. And then no simplification there, no simplification there, plus c. This is one where you could definitely take u to the 6th out of everything, but then you would still have a u squared left over, and I don't really want to expand that, so I'm actually just going to replace every u that I see with 1 minus x, and I'm going to rearrange it so that it goes from highest to lowest power. So I do think a calculator might give you a different answer on this, but I don't really think it's worth our time to try to match that answer because I'm confident that this is right. And those are the choices that you have to make, right? We found an antiderivative. It didn't specify a type of form that we needed for it. So let's take a look at another problem. Number 13, it's going to be the integral of 4x plus 3 over radical 1 minus x squared dx. I'm thinking right off the bat that 1 over radical 1 minus x squared would be arcsine. So I feel like there's going to be an arcsine involved here. And there's a sum in the numerator. So what I'm going to do is break this into 2 integrals and deal with each of them separately. Or hope to deal with them separately. So we have this. And we have this. And that second integral is really nice because I already know it. It's going to be 3 times arcsine of x. So I'm not worried about that at all. So all of my work is going to be devoted to doing that first integral, which I'm going to do by substitution. I have a weird thing in the denominator, so I'm going to let u equal the thing inside the radical and hope that that helps. So from here, I can find that du is negative 2x dx. I definitely in the problem have an x, actually I have 4x, but I'm going to bring that negative 2 to the other side. Say negative 1/2 du is equal to x dx, and use that to make my substitutions. So I will be taking the 4 out of the integral, and then just dealing with x dx over radical 1 minus x squared. So x dx is negative 1/2 du, so that's negative 1/2. I'll put in the du at the end. And then I get 1 over radical u, but I'll make that u to the negative 1/2. And then the du is there. And then plus 3 and this thing, but I already know what this is, so this one's not causing me any stress. Okay, so let's do this. So 4 and negative 1/2 gives me negative 2, and then reverse the power rule, so add 1 to negative 1/2 gives you positive 1/2. The reciprocal of that is 2, so we get 2u to the 1/2. And then plus 3, let's just finish this, arcsine of x, plus c. So this is weird because we have x's and u's, but I mean sometimes that happens and you can't avoid it. Alright, so this is negative 4, u is equal to 1 minus x squared to the 1/2, plus 3 arcsine of x, and then plus c. Okay, so that's 13 problems so far. Let's take a look at a new one. Number 14, square root of x minus 2 over x plus 1 dx. Alright, so this one, I would like to get rid of that radical, so I'm going to do that by substitution. I'm just going to say that u is equal to the entire radical and see what happens. So sometimes you go down a road, it doesn't work, and you have to start again. I think this is going to work, but that's just good advice. If what you're doing is making things more complicated, maybe go back and try something else. So let's square both sides of this. U squared is x minus 2. Let's solve that for x, because I'm going to have to substitute for the x in the denominator. So that's one substitution we'll make. And then let's find a du, or a substitution for dx. So 2u du is dx. We will substitute that. All right, let's do all of our substitutions. Integral of, so square root of x minus 2 is u, so it's u. And then we said that x is u squared plus 2, so x plus 1 is u squared plus 2 plus 1, so that's over u squared plus 3. And then dx, never forget to substitute for dx. That's the biggest mistake people make, is going to be 2u du. And so this becomes 2, and then we have u squared over u squared plus 3 du. I'm going to use a little trick on this that I use on these all the time to just like not do the division. So what I'm going to do in the numerator is I'm going to add 3 and subtract 3, which is like doing nothing, but it turns it into something we can simplify really quickly. I use that to avoid division like all the time. I call it the +1 -1 trick, and there's a separate video on that if you're interested. So we have 2. So it's u squared plus 3 minus 3 over u squared plus 3 du. So the advantage of this is that u squared plus 3 over u squared plus 3 is 1, and then we're just left with minus 3 over u squared plus 3. So let's do that. So we have this. So this is looking like, I'm going to break it up, but it looks like we have just 2u, and then we have an arctan type thing happening. So this, I'm going to divide everything I see by 3 and make it look exactly like an arctan derivative. So du over 1 plus u over root 3 squared. So you can expand that and see it's the same, but we've done that multiple times now. You do it all the time. I need a, so I mean you can just integrate the first part and get 2u. And then, so there's going to be I need a 1 over root 3 on the inside. If I let w equal u over root 3, then dw is 1 over root 3 du, so I need a 1 over root 3, and then to balance that, I'm going to put a root 3 on the outside. So now it's minus 2 root 3 perfect arctan. So that's usually my goal when I'm dealing with arctans, is to just like make it look perfect so I can just go backwards and get the answer immediately. And if we do our substitutions, every u that you see is actually a radical x minus 2. So we get this. It's not pretty, but I mean, why would you expect it to be pretty when the original is kind of weird looking? Okay, so we have that. So that's 14 down. Let's take a look at number 15. Number 15 is the integral of the quantity natural log of x to the 4th all over x. So if you do enough of these and you see a natural log in a problem and an x in the denominator, you start immediately thinking, I should probably let u equal natural log of x. And that's because du will put an x in the denominator. So let's see if that works, which I'm feeling really good about. I think it's going to work. Get this. Let's go right to du. So du is 1 over x dx. We'll make that substitution. So this whole integral, which looks weird to begin with, actually just becomes u to the 4th du, which is great because we can just reverse power rule and get 1/5 u to the 5th plus c, and then do the substitution. I think it's a good idea to put parentheses around the whole natural log thing so that you don't confuse it as like the quantity natural log of x to the 5th versus natural log of x to the 5th. So I always put those parentheses there just to avoid that. I think it's a good idea. All right, let's move on to a new problem. We've got the integral of 3. So that 3 is a little weird. Maybe it'll come into play, or maybe it's just there to, be annoying. So the integral of 3x to the 5th root x cubed plus 1 dx. Okay, so I see that radical thing, and it's worked in the past, so I'm just going to let u equal the whole radical and see what happens. So we have this. I'm definitely going to square this, and then I guess manipulate it a little more. I'm going to solve for x cubed. So x cubed is u squared minus 1. So from here, I think I'm going to end up substituting that. But from here, I'm going to find that 2u du is equal to 3x squared dx. Okay, so that 3x squared dx is there. It's in the problem, right? But we have a 3x to the 5th, so that's 3x squared times x cubed. So let's rewrite that. So 3x squared, and then times x cubed, and then we have radical x cubed plus 1 dx. So that means I'm actually going to, so 3x squared dx is just going to end up du. So this part and this part, that'll be, well, that's going to end up 2u du, I should say, because we can directly substitute for it. The x cubed that's there, I'm going to use u squared minus 1. So I'm going to start with just u squared minus 1. And then the radical thing is u. And then 3x squared dx is 2u du. And now a complicated looking thing ends up looking relatively simple. I mean, I don't know if any of them are really simple, but it's relatively simple. So, combine everything. Let's reverse the power rule a bunch. So 2/5 u to the 5th minus 2/3 u cubed plus c. This is definitely one of those problems that kind of forks. You have a choice. You can directly substitute at this point to get this, which probably would be written as like to the 5/2 and then to the 3/2 for your exponents instead of like radical into the 5th, but that's the way I chose to do it. Or you can go back here and factor out a u. I'm going to take out 2u cubed, I guess, because that's what we can do. And we're left with a u squared over 5 minus 1/3 plus c. Common denominator gives us 3u squared minus 5 over 15. And then, I guess a substitution. So I'm going to make it u is equal to x cubed plus 1 to the 1/2. So to the 1/2 to the 3rd is to the 3/2. And then here, when you square u, you just get x cubed plus 1. So we're going to have 3x cubed. So it's 3x cubed plus 3 minus 5 gives us 3x cubed minus 2. And there we go. All right, so 16 of them. Let's take a look at the 17th one. Integral of dx over quantity 1 plus root x cubed. Okay, I feel like on this problem you basically have no choice from the start. Like, that thing in the denominator is a big problem, so let's just make it u. U is 1 plus root x. Okay, so I don't want to deal with root x. I want to solve that thing for x. So subtract 1, we get this. Square both sides, and we get that. Okay, and from here we can find something that we can substitute for dx. So 2 quantity u minus 1 to the 1st du is equal to dx. Okay, we're going to make that substitution, and I think it's not going to end up that bad. Let's see. So dx is 2 the quantity u minus 1, and then over u cubed and du. Let's simplify that. So I'm going to take 2 out. U over u cubed is just u to the negative 2nd. 1 over u cubed is u to the negative 3rd du. And we will reverse the power rule all the way through. So plus 1 times the reciprocal gives us this. And then plus 1 times the reciprocal gives us this. And now I'm going to substitute back in for u. And I guess distribute the 2. So negative 2 over 1 plus root x. And then plus 1 over the quantity 1 plus root x squared plus c. And I don't think that'll look any better if we combine it, so I'm definitely just going to leave it that way. All right, new problem. So number 18 of 21, we're going to do 21 problems. So integral of radical x to the 4th over x cubed minus 1 and then dx. I find that these radicals with rational functions in them just look scarier than they actually are, but they definitely look scary to begin with. That x to the 4th inside a square root, like that could be simplified. So let's simplify that and see if it helps us to clarify what's going on here. So we actually just have this, and this feels like a problem that we've done before, right? We have a radical thing that's causing problems, so let's make it u and see how it goes. So we have this. Okay, I'm going to square both sides. So it's like at this point you might be worried about that x squared that's in the numerator of the integrand, but when we find our dx, it's going to come along with an x squared. So we get 2u du equals 3x squared dx. I don't actually have a 3 in the original problem, I just have x squared in dx, so I'm going to bring the 3 to the other side and get 2/3 u du is x squared dx. And let's do our substitutions. So we get 2/3 u du is substituting for x squared dx, and then over just u. And so this is crazy. this is actually just 2/3 du, which is definitely just 2/3 u plus c. So it looked really scary to begin with, but once you did the algebraic manipulations and the substitution, it gets crazy simpler. And so we end up with 2/3 the square root of x cubed minus 1, and then plus c, and that's it. All right, let's take a look at number 19 of 21. We're almost there. Okay, integral of dx over root x, quantity 1 plus x. So on this one, it's like not immediately obvious what to do. Like maybe you would want to like distribute or something. I prefer to get rid of radicals when they're in problems, so I'm just going to let u equal that radical x and hope it works. So square both sides. And from here, we can definitely get something for dx, right? So it'll be 2u du is dx. And all right, let's do it. Let's substitute. So dx is 2u du. Radical x is actually u, so that'll be u. And then quantity 1 plus u squared, because we said x is u squared. So I should have boxed that when I got x equals u squared, but that's okay. Substitute there. This simplifies to 2 du over 1 plus u squared. And this is actually the most straightforward arctan that we've had in all of these problems, because it's basically done. So it's 2 arctan of u. And then plus c, and replace it, and that problem is done. So that problem is actually simpler than it looked initially. You just have to like think what to do. And so I would, I have a preference for getting rid of radicals if I can. If it had been the quantity 1 plus x to like the 35th power, I don't know what I would have done. I mean, I would have made u equal 1 plus x because there's no way I want to expand that. And then I just would have hoped that it worked. But in this case, getting rid of the radical right away, good move. Let's take a look at a new problem. All right. Integral of x cubed, quantity x squared minus 1 to the 3 halves. So something to the 3 halves is kind of annoying no matter what it is. But when it's x squared minus 1, I would like to simplify that. So I'm going to say that u is x squared minus 1. And so let's do our thing. We can find du straight from here. So du is going to be 2x dx. And that means, all right, so if you look at the original problem, like we definitely have an x that we can use and a dx. It's just that we have x squared times x because we have x cubed, but let's not worry about that. Like that's good. We don't have a 2, so I'm going to rewrite this as 1/2 du is equal to x dx. And we'll make that a substitution. So I'm going to rewrite the integrand a little bit because here x squared is equal to u plus 1. And we can rewrite the integrand as x squared, quantity x squared minus 1 to the 3 halves, and then times x dx to make it like a little more explicit what substitutions we're doing. So here, x squared is u plus 1, and then x squared minus 1 is u from like our initial premise, and then so that's u to the 3 halves, and then x dx is 1/2 du. Okay, let's simplify the integrand. So I'm going to pull 1/2 out and distribute. So 1/2 integral, so we get u to the 5 halves plus u to the 3 halves, and then du. And it's a lot of reversing the power rule, well, 2 times. So plus 1 times the reciprocal, and then plus 1 times the reciprocal, and then plus c. And this is definitely one that looks like it could go either way, right? Factor u to the 5 halves out, or just directly substitute. So I always like to just directly substitute to begin with. I am canceling the 1/2 with the 2's in the numerator. So we get this, which I think is a perfectly fine answer. It's like, there's definitely a critical point. Well, actually, we're not taking derivatives, so I don't even know. This is fine. But I do think that technology would probably factor. So we factor, and then we get this. So generally speaking, like you usually factor because you're looking for critical points of a derivative, and I got confused halfway through there, and that's why I started talking about critical points. But no, we're doing antiderivatives, not derivatives. So we get this, common denominator here. And then we know that u is actually x squared minus 1. So 5x squared minus 5 plus 7 is 5x squared plus 2. All over 35, and then plus c. So those always have like the two paths you could choose to take. Totally up to you which one you go for. All right, and number 21. 21 is actually a weird problem. So we have the integral of dx over 2 root 3 minus x root x plus 1. So this is, it's not really a nightmare because it's just going to work out, I think, as long as we don't make mistakes. But there's two radicals in the denominator. So we have to decide what to do. Of the two radicals, I think I dislike radical 3 minus x more than I dislike radical x plus 1 because of that like minus x situation. So I'm going to choose to let u equal that radical. So u is equal to radical 3 minus x. And that means square, what am I doing? Yeah, I'm going to square both sides and then solve for x. So x is equal to 3 minus u squared. Right, you get u squared is equal to 3 minus x. Add x to both sides, subtract u squared from both sides, so we get that. That we are going to substitute for because the radical x plus 1 has an x in it that we need to account for. And then from there we can find a dx. So dx is negative 2u du. And we're going to substitute that. So let's do our substitutions. So dx, negative 2u du. There's a 2. And then that radical is just u. That was the whole idea. And then, so x is 3 minus u squared. So we have 3 minus u squared plus 1. So 4 minus u squared. So it's radical 4 minus u squared. Which isn't bad because that looks like an arcsine type of thing. So let's simplify this. Take out the negative. And we have this. Okay, so if I take 4, I'm going to factor a 4 out of everything in the radical. That'll be for the quantity 1 minus u squared over 4. Square root of 4 is 2, so you actually can take a 2 out of the radical. Like this. And 1 minus. I'm going to make it the quantity u over 2 squared. Just like with arctan, we try to like match a form. And so this, I'm going to turn into 1/2 du. And then got radical 1 minus u over 2 squared. Okay, that's actually a perfect arcsine, right? If I let w equal u over 2, then dw is 1/2 du. And we would have dw over radical 1 minus w squared. That's arcsine. So this is actually negative arcsine of u over 2 plus c. And then u was that radical. So that's negative arcsine of radical 3 minus x over 2, and then plus c. Okay, so that's the answer, but you might say, like, why did I use radical 3 minus x other than the fact that I didn't like the way it looked? There wasn't really a good reason. So actually, we can redo the whole problem and choose the other radical. So if we do that, it's really similar. So I'm going to square and solve for x to get this. I'm going to end up substituting that. I'm going to find dx is 2u du. So things are like really similar, but a little bit different. Let's do all the substitutions. So we'll get 2u du, and then over 2, and then it's 3 minus x, and x is u squared minus 1. So it's 3 minus u squared plus 1, so 4 minus u squared, which looks really familiar. And then that was u. Simplify this to get this, and then do the same work that we did, right? We're taking a 4 out of everything in the radical, and then radical 4 is 2, and then we rewrite it so it looks like arcsine, and then I'm going to bring that up. So the 2 in the denominator I bring up is 1/2 in the numerator. It's kind of a reverse of something that you do a lot in like algebra. You do that a lot in calculus, like weird reversals of algebraic steps. And then this is a perfect arcsine. So we get this, then plus c. And then we do our substitution. So we get this. So it looks like we're going to end the video on kind of a mystery, because it turns out that negative arcsine of radical 3 minus x over 2 plus c is somehow equivalent to arcsine of radical x plus 1 over 2 plus c. And the secret is in the plus c's. So if you take both of those and graph them, just let c equal 0, you'll see they're actually just vertical shifts of each other for some reason. I haven't done a proof or verified that yet, but it's definitely the case. I did graph it and take a look at that. So that's 2 ways you could have done it. That's a lot of problems. I hope you found this helpful, and good luck.